If I offered to sell you this dollar for $1.05, you'd probably walk away because you know that spending a premium on cash is a mistake. But millions of people take that exact deal every single day through parlay boosts. They think they're boosting our winnings, but in reality, our models show that they're actually multiplying the house's edge. And as they add additional legs to their parlays, well, this dollar is now $1.40. We are Team 19140, and today we'll present our solution from the perspective of people without their sports hats on the rise of online gambling, what's at stake. Our first model asks, before anyone places a single bet, how much money can they actually afford to lose? We input salary, age, and demographics and get a return of an investment or an estimate of a person's disposable income. We have 5 assumptions to ground this model. First, we use 2024 tax systems from both the US and UK, assuming single filers with a standard deduction. This is conservative because it overstates tax burden. Only genuinely non-discretionary categories are included in essential expenditures like food and housing, excluding entertainment. This gives us a lower bound on true costs. We also use mean income from BLS survey data, which exceeds the median in right-skewed distributions, making our vulnerability estimates conservative. Negative disposable income is tracked as a debt accumulation rate, not represented as a zero floor. This model combines deterministic components like salary and tax obligation with stochastic components like your essential living costs, resulting in a full distribution of financial capacity for each demographic group, which lets us identify vulnerabilities that averages would miss. The core equation is that DI equals gross income minus taxes minus essential costs. The first 2 terms are deterministic, set by tax law, and the third term is stochastic, drawn from a right-skewed log normal distribution whose mean matches BLS data for each age group and region. You can see our defined variables in the table, and the critical outputs are disposable income, which may be negative, and delta, the debt accumulation rate. For the tax function, we implement the 2024 tax bracket system. 7 progressive rates are applied marginally, including FICA contributions and national insurance. We run against 3 archetypes to test whether our conclusions depend on state tax policy. Texas at 0%, Illinois at a flat 4.95%, and California's marginal rate at 13.3%. Essential spending is the sum of 6 categories, each passing a simple test. Could a reasonable person choose to spend 0 on this? Food and housing clearly cannot be eliminated. The stacked bars in the shown graph show essential expenditures by age group, and the black line shows mean gross income. Notice the gap between income and expenses nearly vanishes for the youngest and oldest age groups.
So here's our disposable income results by age group using Illinois as our baseline. 3 age groups are already in the red, as you can see there, under 25, 65 to 74, and 75 plus. The typical person in these cohorts spend more than they earn even before gambling enters the picture. And even in the comfortable 45 to 54 group, someone in the top 10% of essential costs only has $4,100 left, over a $9,000 swing from the median, and that's why a deterministic model isn't enough. The 45 to 54 group sits at the financial sweet spot with about $13,100 in disposable income. But for under 25s and for 65 plus, the median falls into the debt zone. The most striking statistic is that 62% of under 25 earners are already in deficit before they even place a single bet. Young adults who gamble aren't gambling with surplus money, they're gambling with financially constrained resources. The same pattern holds across for Texas, Illinois, California, and the UK. So a few key takeaways. First, the youngest and oldest cohorts have the smallest financial cushion, and they're exactly the groups with the highest gambling participation or the least ability to recover from losses. Second, within group costs, variation drives vulnerability, which means that many income-based limits alone would miss many precarious moderate earners. A plus or minus 10% change in income shifts disposable income by $6,500 and housing by $2,650. State tax has the least effect at just $495, confirming that this is a demographic phenomenon. And when we increase the expenditure variability parameter from 0.3 to 0.4, the under 25 deficit rate rises from 62% to 71%, meaning that our findings are actually conservative. The core results hold under every perturbation and is validated against BEA data. The model strength is built entirely on authoritative government data, and stochastic approach captures within group variation deterministic models miss. Its main limitation is a single earners assumption, which overtakes tax burden for dual income households. Access to BLS microdata and household composition modeling would refine it further. So Q1 told us who is vulnerable, and now Q2 will tell us how much they stand to lose. Our stochastic gambling outcome model simulates 10,000 bettors over a full year using Monte Carlo methods. The model rests on 5 key assumptions as you can see here. The most important one is at the top. The house always wins. For every dollar wagered, the sports books keeps about 10 cents, which is backed by real industry data. We classify bettors into 3 risk profiles: conservative, moderate, and aggressive, and each one plays out for over a full simulated year. The third point is what makes this model interesting. A coin flip doesn't care about the last flip, but the bettor does. When someone loses, they tend to bet bigger to overcome their loss. Over half of bettors reported doing this, so we built a Markov chain to capture that feedback loop.
This table maps every variable to its source. Account rates and bet frequencies come from the Siena survey, and the house edge comes from AGA industry data. Stake sizes are drawn from an exponential distribution because bets are usually small with occasional larger ones, matching observed patterns. The behavioral state determines whether someone is betting normally or chasing losses. Every sports bet has a negative expected value equal to negative b times h, where b is the stake size and h is the house edge. We classify bets into 3 archetypes. Conservative covers standard point spreads at 4.8% edge, moderate covers small parlays at 10%, and aggressive covers multi-leg parlays at 25%. When you chain bets into a parlay, the house edge compounds. This justifies our archetype edges. Moderate bettors place 2 to 3 legs and land around 9 to 14%, and aggressive bettors place 5 to 7 legs and land around 22 to 29%. Bets are not independent because people naturally adjust their stakes based on recent outcomes. When someone loses, they bet more to compensate, a phenomenon known as loss chasing. We modeled this with a 2-state Markov chain, a normal state where bettors play at baseline stakes, and a chasing state where stakes increase by 50%. Aggressive bettors, who only win a fourth of the time, end up spending more than half their betting life at elevated stakes, creating a damaging self-reinforcing feedback loop. We simulate 10,000 virtual bettors through a full year by drawing random stakes, determining outcomes, and transitioning Markov states. The result is a complete distribution of annual outcomes, including the tails which become relevant in question 3. We run 2 versions of the model, a standard version with no loss chasing and a chase version incorporating the Markov chain. Loss chasing amplifies expected losses by 35% consistently across all groups, and this happens because amplification is driven by the win probability and the Markov transition probabilities. What does vary dramatically is engagement. Males aged 18 to 34 bet 4 times more frequently than males who are 65 and older, producing a 12-fold difference in expected annual losses. Conservative and moderate bettors cluster more tightly, with lower mean losses and lower variability. Aggressive bettors, on the other hand, have higher potential payouts, but their variability is dramatically larger, making catastrophic losses a very real possibility. The deceptive part is that 42% of conservative bettors finish any given year in profit. Over 1 year, luck can mask the edge, but over many years, the math always takes precedence. First, bet type corresponding to house edge dominates. Second, loss chasing creates a self-reinforcing cycle that amplifies losses. And third, short-term luck consistently masks long-term certainty, which is why so many bettors continue to play. Our tornado chart confirms a hierarchy across 3 tiers. Structural factors like house edge beat behavioral factors like loss chasing, which in turn beat volumetric factors like bet frequency or stake size. Our model has several strengths. It produces full distributional outputs, incorporates parlay edge compounding, and the Markov chain captures the often masked interaction between outcomes and subsequent behavior. The weaknesses are that the 2-state chain oversimplifies dynamic human behavior, and our parameters come from self-reported surveys. Refinement would involve access to real sportsbook data, extension to more Markov states, and the inclusion of promotional credits.
We now bring Q1 and Q2 together to quantify the impact of gambling spending in terms the general public can understand. To do this, we built 3 complementary metrics. For assumptions, our threshold for financial distress is when annual gambling losses exceed 10% of disposable income. That level is associated with debt accumulation, according to consumer finance research. We also assume that losses come from disposable income rather than borrowing. In reality, problem gamblers often borrow at 20+% APR, so our estimates are conservative and true harm is likely worse. Here are our 5 key variables that we'll be using for the rest of Q3. Now onto the 3 metrics we made. The simplest one to quantify impact would be the gambling drain ratio, which we define as annual loss divided by disposable income. However, that single number throws away everything we worked to produce in Q1 and Q2. To Two bettors can have the same average loss, but one can have more variance than the other, say losing 200 in one bet and then 4,000 in the next. That bettor is so much more likely to have a catastrophic year where they end up in debt. Since the GDR is blind to this, we built the PFR, which looks at all 10,000 of her simulated outcomes and checks, did this person cross the 10% threshold? For the wealth erosion model, we basically just took the long-run value of the L of H sub T term, which was made in Q2. It shows that every dollar lost to gambling is a dollar you could have invested, and that investment grows at 7% rate year over year. Now here are the 67-to-1 ratio visualization. We see that for every dollar of public revenue generated, nearly $67 has to disappear for someone's bank account. We got this value by looking at one scenario. Let's say a bettor loses $1,500. The sportsbook then takes 10% of that, $150 as profit. Then the state taxes that $150 at 15%, earning $22.50. $1,500 over $22.50 is 67-to-1. And state lotteries use a ratio of 2-to-1, showing how inefficient online sports gambling truly is. Now for the results of the PFR model. Look at males 18 to 34. By just the GDR, we'd say that only 15.6% were in a dangerous position. But the PFR shows us that that number is closer to 38.2%, more than a third. And look at the results of the wealth erosion model. We see that a moderate bettor starting at age 22 accumulates nearly $131,000 in opportunity costs over 30 years. That is 7 times the median retirement savings for Americans.
For the majority of bettors, about 26 million Americans, gambling is manageable entertainment. But for approximately 4 million Americans and 2.1 million in the UK, the annual probability of financially dangerous losses exceeds 30%. Populations most financially vulnerable in Q1 overlap almost perfectly with the heaviest gambling demographics in Q2. And when we combine both models in Q3, the same group produces a 38.2% probability of financial ruin. This overlap is not coincidental, and it reflects the targeted marketing of sportsbook apps towards the demographics least able to absorb losses. Our framework shows that targeted interventions could protect this most vulnerable 10% without burdening the 65% for whom gambling remains affordable entertainment. A plus or minus 10% change in house edge shifts the PFR for males 18 to 34 by about 5 percentage points, and reducing the investment return assumption from 7% to 5%, lowers 30-year wealth erosion from $131,600 to $96,200. And if we tighten the ruin threshold from 10% to 5%, PFR rises to roughly 52%. If we relax it to 15%, PFR drops to about 28%. Under every tested perturbation, it's clear a substantial minority of bettors facing dangerous annual financial risk. Now onto our performance analysis. In terms of strengths, the PFR integrates the full distributional output of both Q1 and Q2, capturing tail risk. The dynamic wealth erosion model uses age-varying losses from Q2, avoiding the unrealistic assumption of constant annual losses. But the weaknesses come with the PFR, as it assumes gambling losses are financed from disposable income. In practice, problem gamblers often borrow to gamble, which would make actual harm much worse than we predict. The 10% threshold is motivated by consumer finance research, but it is inherently somewhat arbitrary. And the 6:1 ratio uses the average state tax rate of 15%, where some states may vary. For refinement, incorporating actual borrowing behavior would capture the full financial cost. The binary 10% cutoff could be replaced with a continuous harm function. And adjusting the ratio for state-specific tax rates would enable state-level policy recommendations. We wanted to make sure that our calculations made an impact beyond just this competition. So we reached out to Dr. Jamie Costello, the Associate Director at the National Council on Problem Gambling, and we walked her through our paper. A lot of what we found aligns with what her organization is already advocating for. The recommendation we made for income-linked deposit limits already exists in the UK, and adapting it for the US is an active priority, though state-by-state regulation makes it a real challenge. To summarize, our disposable income model reveals that 62% of under 25 earners are already in debt before gambling enters the picture. Our stochastic gambling outcome model proves that parlay edges compound exponentially and that loss chasing creates self-reinforcing cycles. And our financial impact assessment shows that more than 1 in 3 young male bettors face financial ruin each year, that 30 years of moderate betting costs equivalent to a retirement, and that sports betting returns just $1 to the public for every 66 it takes from individuals. We recommend income-linked deposit limits, restrictions on parlay promotion, and mandatory cooling off periods after large losses, as well as enhanced disclosures for users under 25. Thank you so much for listening.
I can start with a question. One thing I loved about your paper was that you dove deep on this parlay question, which is a big part of the. I think as you figured out by talking to this woman at the National Council, it's a big part of the conversation on restricting gambling. But we actually didn't hear that many details about it. So maybe you could give in your own words what is a parlay, what's a parlay chain, and why do these have such a big impact on how much individuals lose?
So, hello. So from our understanding, a parlay is just a chain of multiple different bets. So that you need to win all to get money back. So for example, if there's a 10-leg parlay, you would have to win all 10 bets to make a profit. So the thing with parlays is that, and this ties into our 3 different archetypes, bettors bet differently. So some conservative bettors, they only like bet on one thing, but other like more aggressive bettors, they're gonna bet on like multiple different things and try to chase higher profits. So our sort of like understanding of the parlay is that as more and more like legs are bet on, the house edge, it starts like compounding multiplicatively, and that changes the house edge in sort of an exponential rather than a linear fashion. And this sort of like contributes to the house edge differences and the like, and in turn the expected annual losses between the 3 different archetypes of the bettors.
Yeah, great. That explains it perfectly. Thank you.
My question is about tax revenues and public harm. So you talk a lot in your model about that. So if you were challenged by a politician, what are the key points that you could argue with, bring it up, like why policies should change to prevent people from losing money? Thank you.
Yeah, definitely. So one thing, I'm putting it up on the slides right now, the 67-to-1 ratio. Oh yes, definitely. So what a lot of politicians argue pro like online gambling is that it generates some revenue for the state. However, this 67-to-1 ratio shows that even if it does generate revenue, every $1 that the state gets, $67 has to disappear from someone's bank account. And state lotteries have a ratio of 2-to-1, which is, so this clearly shows that online sports gambling is so much more inefficient and that we can't justify that the state earning some money from taxes is a reasonable way to keep this implemented.
I
Thank you.
got a little lost in the calculations here. So why do we have this drop from, if I lose $1,500, that's not what I bet, that's what I actually lose. Why do we then drop to a 10% in terms of sportsbook revenue?
1,500 is what you lose, and then 1,350 goes to other bettors. But the sportsbook takes 10% of that 1,500, so they earn 150 as profit. Then the state taxes that 150 at 15%. So the state earns $22.50 at the end of the day, which we're saying is the public benefit. But the individual had to lose 1,500 for that to happen.
Sure, but I think I would use the wording the individual had to bet 1,500, because if
Yeah.
1,300 is going back to other bettors, in some sense that is going back to the public, right?
Definitely, that 1,350 can be like incorporated into taxes on those people's income. But another thing we realize is that if those other bettors who won this bet lose money, they could claim deductions on that 1,350. So we don't know if there's like a net gain in the state revenue from that 1,350 at the end of the day.
Okay, so maybe there's like a more complicated calculation that could happen with more time and data. Okay, thank you.
Yeah, we'll definitely look into that for our future calculations if we expand on this.
So in your model, you said the amount of the bet and the frequency of betting you kept as being independent. Is that correct? But you also, one of your big points here is that this chasing has a big impact. Can you explain why you decided to make those things independent and what you might change if you take a second look at it?
So just to clarify, you're just asking why we decided to make the behavior dependent instead of independent. So something that we've seen in a survey is that 52% of bettors, they sort of like chase losses. So that's when they, if they lose, they bet more to try and recover their losses. So this is a very real thing that we can't just, that we should account for, because human gambling, it's not just math, there's also a component of psychology involved. So we believe that sort of incorporating a dependent aspect through a Markov chain to help model that sort of psychological behavior that's very common will sort of give a better estimate of how like much bettors actually lose. And to furthermore, right now we only have 2 states, with one state just being like stakes increasing by 50%. But in reality, human behavior is a lot more dynamic, and like chasing has multiple different avenues. So right now, like since we only have 2 states, that sort of provides a minimum baseline amount of loss. And this just sort of shows like how much chasing impacts a gambler.
Any last questions?
I just have a remark. I just want to commend you on going a step further than beyond this challenge to actually, really live the fact that math modeling and the computing has a real impact by reaching out to the association there and that person. So I really commend you on that. And I guess I do have a question. Like, if you had time, and maybe you will make time, what would you like to do next in your model? How would you like to push this a little further?
So I think one thing we would like to improve is getting access to anonymous sportsbook data, because currently we're assuming that a majority of people will bet low and that only some people will bet high, so we sort of have an exponential curve. But we're not sure if that's actually true because we don't have anonymous data. We have self-reported data, so a lot of the time it's going to be misleading. And another thing, as Shriten said, another thing we'd like to expand on is increasing the number of states we have in our Markov chain, because currently it doesn't fully reflect the psychological behavior of the average bettor. It's mainly just two main states we have, normal and chasing. So yeah, increasing that amount would make our model a lot more accurate.
Thanks so much, guys. So that wraps us for questions. You have 1 minute. If you want to say any thank yous, go ahead.
Yeah. We now just want to thank our school, the Edison Academy Magnet School, and the National Council on Problem Gambling for their support, and MathWorks, Siam, and Jane Street for this amazing opportunity. We'd also like to thank our coach and chaperones, Ms. Gomes and Mr. Roman, as well as our parents back in New Jersey. And of course, thank you to the wonderful judges for listening to our presentation. It's been a long day, but it's been really fun.
Thanks, guys.